There's something special about meteors that collide with Earth, Patrick Schober from Conversation reports. Much of what scientists know about the early solar system comes from meteorites, ancient rocks that travel through space and survive a fiery plunge through Earth's atmosphere. Among meteorites, one type called carbonaceous chondrites stands out as the most primitive and provides a unique glimpse into the solar system's infancy. The carbonaceous chondrites are rich in water, carbon, and organic compounds. They're hydrated, which means they contain water bound within minerals in the rock. The components of the water are locked into crystal structures. Many researchers believe that ancient rocks played a crucial role in delivering water to early Earth. And before hitting the Earth, the rocks traveled through space are generally referred to as asteroids, meteoroids, or comets, depending on their size and composition. If a piece of one of these objects makes it all the way to Earth, it becomes a meteorite. From observing asteroids with telescopes, scientists know that most asteroids have water-rich carbonaceous compositions. Models depict the most meteorites, over half, should also be carbonaceous, but less than 4% of all the meteorites found on Earth are carbonaceous. So why is there such a mismatch? In a study published in the journal Nature Astronomy on April 14, 2025, my planetary scientist colleagues and I tried to answer an age-old question: where are all the carbonaceous chondrites? Sample return missions. Scientists' desire to study these ancient rocks has driven recent sample return space missions. NASA's OSIRIS-REx and JAXA Hayabusa 2 missions have transformed what researchers now know about primitive carbon-rich asteroids. Meteorites found sitting on the ground are exposed to rain, snow, and plants, which can significantly change them and make analysis more difficult. So the OSIRIS-REx mission ventured to the asteroid Bennu to retrieve an unaltered sample. Returning the sample allowed scientists to examine the asteroid's composition in detail. Similarly, Hayabusa's 2 journey to the asteroid Ryugu provided pristine samples of another similarly water-rich asteroid. Together, these missions have let planetary scientists like me study pristine, fragile, carbonaceous material from asteroids. These asteroids are a direct window into the building blocks of our solar system and the origins of life. The carbonaceous chondrite puzzle. For a long time, scientists assumed that the Earth's atmosphere filtered out carbonaceous debris, and when an object hits Earth's atmosphere, it has to survive significant pressures and high temperatures. Carbonaceous chondrites tend to be weaker and more crumbly than other meteorites, so these objects just don't stand as much of a chance. Meteorites usually start their journey when 2 asteroids collide. These collisions create a bunch of centimeter to meter-sized rock-sized fragments, and these cosmic crumbles streak through the solar system and can eventually fall to Earth. When they're smaller than a meter, scientists call them meteoroids. Meteoroids are far too small for researchers to see with a telescope unless they're about to hit the Earth, as astronomers get lucky. But there's another way scientists can study this population and in turn understand why meteorites have such different compositions. Meteor and fireball observation networks. Our research team used the Earth's atmosphere as our detector. Most of the meteoroids that reach Earth are tiny, sand-sized particles, but occasionally bodies up to a couple of meters in diameter hit. Researchers estimate that about 5,000 metric tons of micrometeorites land on Earth annually and every year, and each year between 4,000 and 10,000 large meteorites, golf ball size or larger, land on Earth. That's more than 20 every day. Today, digital cameras have rendered round-the-clock observation of the night sky both practical and affordable. Low-cost, high-sensitivity sensors and automated detection software allow researchers to monitor large sections of the night sky for bright flashes, which signal a meteorite hitting the Earth's atmosphere. Research teams can sift through these real-time observations using automated analysis techniques or a very dedicated PhD student to find invaluable information. Our team manages two global systems, FryPon, which is a French-led network with stations in 15 countries, and the Global Fireball Observatory, a collaboration started by the team behind the Desert Fireball Network in Australia. And together with other open access datasets, my colleagues and I use the trajectory of nearly 8,000 impacts observed by 19 observation networks across 39 countries. By comparison, all meteoroid impacts recorded in Earth's atmosphere with those that successfully reach the surface as meteorites, we can pinpoint which asteroid produced fragments that are strong enough to survive the journey. Or conversely, we can also pinpoint which asteroids produce weak material that do not show up as often on Earth as meteorites. The sun is baking the rocks too much. Surprisingly, we found that many asteroids pieces don't even make it to Earth, sometimes starts moving the weak stuff while the fragment is still in space. The carbonaceous material, which is not very durable, likely gets broken down through heat stress when its orbit takes it too close to the sun. And as carbonaceous chondrites orbit close and then away from the sun, the temperature swings from cracks in their material. This process effectively fragments and removes weak, hydrated boulders from the population of objects near the Earth. Anything left over after this thermal cracking then has to survive the atmosphere. Only 30% to 50% of the remaining objects survive the atmospheric passage and become meteorites. The debris pieces whose orbits bring them closer to the sun tend to be significantly more durable, making them far more likely to survive the difficult passage through Earth's atmosphere. We call this a survival basis. For decades, scientists have presumed that Earth's atmosphere alone explains the scarcity of carbonaceous meteorites, but our work indicates that much of the removal occurs beforehand in space. So going forward, new scientific advances can help confirm these findings and better identify meteoroid compositions. Scientists need to get better at using telescopes to detect objects right before they impact our Earth. More detailed modeling of how these objects break up in the atmosphere can also help researchers study them. And lastly, future studies can come up with better models to identify what these fireballs are made of using the colors of the meteors. This is by Patrick Schober, postdoctoral fellow, Planetary Sciences, NASA, on the conversation under Creative Commons on Science Alert. Please leave your comments and thank you for your support. Please support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.